These 12 ordinary English words, army, van, defense, carry, jealous, true, garbage, claim, echo, media, make, crunch, encode exactly the same information as this hex blob. One you can memorize, one you can't. Today we trace how a random number becomes your seed phrase and why those words aren't actually the seed your wallet uses. First, a crucial point. You don't pick these words. The wallet picks them because humans are catastrophically bad at randomness. Entropy, true unpredictable data, comes from the wallet's random number generator, not your imagination. Brainwallets, where users invent their own passphrase, have been drained repeatedly. BIP39 fixes this by flipping the process. The machine generates the bits, then translates those bits into words you can write down. Here's the recipe. Step 1. Generate 128 bits of entropy, a random binary string. Step 2. Hash that entropy with SHA-256, a standard cryptographic hash function that produces a 256-bit fingerprint. Take the first 4 bits of that hash. This is the checksum, a built-in error detector. The rule is the number of checksum bits equals the entropy length divided by 32, so 128 divided by 32 equals 4. Step 3, append those 4 checksum bits to the original 128, giving you 132 bits total. All right, that checksum is why a typo in your seed phrase fails validation. Instead of silently producing the wrong wallet, it catches most single word errors before they cost you anything. Step 4, slice those 132 bits into chunks of 11 bits each. 132 divided by 11 equals exactly 12 chunks. Step 5, each 11-bit chunk represents a number between 0 and the 2047, which indexes into a fixed dictionary of 2048 English words. 2 to the 11th power equals 2048, and that's exactly why the word list is that size. For example, chunk number 1019 becomes the word army. Chunk number 1039 becomes van. 12 chunks give you 12 words. That's the entire encoding. Now let's scale this idea up and look at the full BIP39 table. 128 bits of entropy plus a 4-bit checksum gives 132 total bits, which divides into 12 words. 160 bits plus a 5-bit checksum gives 15 words. 192 plus 6 gives 18 words. 224 plus 7 gives 21 words. And 256 plus 8 gives 24 words. The pattern fits a single formula. Entropy plus entropy divided by 32, all divided by 11, equals the word count. Every wallet you've ever used, Ledger, Trezor, Electrum, Sparrow, follows this exact table. That's the reason a seed phrase generated in one wallet will restore perfectly in another. But here's the twist. Those 12 words still aren't what your wallet uses to generate keys. The words get fed into a function called PBKDF2, password-based key derivation function 2. It takes your mnemonic as input, uses the literal string of mnemonic, plus any optional passphrase as salt, and runs 2048 rounds of HMAX SHA-512. HMAX SHA-512 is a keyed hash producing 512 bits. Salt is extra data mixed in to prevent pre-computed attacks. After 2048 iterations, the output is a 512-bit seed. That seed, not the words, is what feeds BIP32, the hierarchical deterministic wallet standard that derives every private key in your wallet tree. The words are just a portable encoding. The seed is the real cryptographic root. Why only 2048 rounds? It's a compromise. Key stretching, running the hash many times, slows down attackers who try to brute force weak inputs, but BIP39 has to run on resource-starved hardware wallets, so the count stays low. Compare with ACID, Lightning Labs alternative, which uses 32,168 rounds of script, a memory hard function, far tougher on attackers. BIP39's weak stretching mostly helps in partial compromise scenarios, say an attacker recovers 11 of your 12 words. Against a full brute force of strong entropy, 2048 rounds are essentially cosmetic. The real security is the entropy itself. Now, the passphrase trick. The optional passphrase goes into the salt. Same 12 words with no passphrase produces one 512-bit seed. Same 12 words with passphrase super duper secret produces a completely different 512-bit seed, a completely different wallet. And here's the landmine. Every passphrase is valid. There's no such thing as a wrong passphrase. A typo doesn't throw an error. It silently derives a different empty wallet. This enables plausible deniability. You can keep a small decoy wallet with no passphrase and your real funds behind the secret one, so a coerced attacker sees only the decoy, but forget your passphrase or die without recording it, and the coins are gone forever. No recovery, no support line. So is 24 words twice as secure as 12? Not meaningfully. Bitcoin's public keys live on the SEC PU536K1 elliptic curve, which offers 128 bits of security strength. That means the best known attack against a Bitcoin public key costs roughly 2 to the 128 operations. Astronomical but finite. 12 words gives you 128 bits of entropy, which matches that ceiling exactly. 24 words gives you 256 bits of entropy, but the curve itself caps effective security at 128 bits. You can't be more secure than the weakest link. Extra entropy only pays off in partial compromise scenarios. If someone photographs half your seed, a longer phrase buys you breathing room. But for a clean, uncompromised backup, 12 words is cryptographically sufficient. Zoom out. BIP39 is a human interface to cryptographic randomness. Every design choice is a compromise. Weak key stretching, so cheap hardware signers can run it. A fixed 2048-word English list, so any wallet can decode any seed. An optional passphrase, so users get deniability at the cost of silent failure. A 4-bit checksum, enough to catch common typos, not enough to resist adversarial tampering. Understanding these trade-offs reshapes your backup strategy. Option 1. Protect the 12 words absolutely. Steel plates, geographic redundancy, treat paper as temporary. Option 2, split them using BIP39, which shards the mnemonic into Shamir shares, so no single location holds the full secret. A passphrase is simultaneously your strongest defense and a single point of catastrophic loss. Use it only with a serious inheritance plan. Every modern HD wallet inherits this pipeline: entropy, checksum, words, PBKDF2, 512-bit seed, BIP32 tree, billions of derivable keys. The 12 words in your safe aren't just a password. They're the entry point to a deterministic universe of addresses, and now you know exactly what happens between writing them down and signing your first transaction.